Let's look at this issue a little bit more closely. Unfortunately, when we do diagnostic testing, we typically deal with imperfect tests. So let's see if we can quantify what we mean by imperfect tests, and let's see what the consequences are of having an imperfect test. Here's an example. Suppose we want to use X-rays to screen for tuberculosis. Here is a study done for this test. So of 30 people who had their X-rays taken, who had tuberculosis, we see that 22 of those 30 tested positive. Unfortunately, 8 tested negative. So this is what we call false negatives. Now, if we look at the proportion who tested correctly of the people with the disease, we call that the sensitivity. So in this case, the sensitivity is 0.7333. So this is an estimate of how accurate this method of detecting tuberculosis is when we apply it to people with tuberculosis. So now, what about the other people? What about the people without tuberculosis? What happens when we test such people? And so what we do is take a look at a sample of such people. And here what they did is they chose 1,790 people, took their X-rays, and found that 1,739 of them tested negative, as they should. Unfortunately, 51 tested positive. So that's what we call the false positives. So there were 51 false positives, then 1,739 who got the correct answer, well, we got the correct answer for. That ratio, 1,739 divided by the 1,790 who were tested, is what we call the specificity. So the specificity in this case was 0.9715. So pretty good, 97%, more than 97% tested correctly, where the answer should have been negative. That's what we call the properties of the test. This has got nothing to do with applying this test just yet. So this is before we do the testing, we can establish how accurate our test is. And we expect it to act differently on people who have tuberculosis, and that's the sensitivity. And then again on people who don't have it, and that's the specificity.